Swayam Prabha. Digital India. Educated India.
In the previous lecture, we learned a lot about PN junction diodes, how they are created, and what's the transport mechanism, the current transport mechanism that's happening inside the PN junction. Now, in this lecture, we are going to use the PN junction diode in a circuit. So, to begin with, we'll start with a simple model, which is a constant voltage model, and then we will do a few circuits, single diode circuits, to go through some foundation of how do you make circuits using diodes. I'm also going to teach you about how to analyze these circuits. And one key point we are going to go over again in this lecture, which is really important, is how do you do DC analysis and then how do you do small signal analysis. I know that many of you are still a little confused about that, so we will go through a detailed example of DC analysis and then following AC analysis. We will also do a numerical example, because only when you go through a numerical example, you can really understand the idea completely. Now that we have learned how the PN junction diode works, what is the IV characteristics of the PN junction, we are going to, every time we cannot use that equation to solve circuits. So we will simplify the device equations into models, and then we will use the models to analyze circuits. So the very first model we are going to talk about is called constant voltage model for diode. In this model, what we are assuming is the following. Okay, this is voltage across the diode here, VD, and this is the current flowing through the diode. In this model, the characteristics of the diode is as simple as this. Let me use a different color. I'm going to use green color here. The characteristics is, this is VD on, where the diode fully turns on. So it's an extreme model, but it can work for simple cases. Okay. So let's first, I would like you to exercise is what is the resistance of the diode in this particular case. So this is the model, visual model of the diode. For voltage VD across the diode, you get current ID flowing through the diode. Only when voltage across the diode is beyond VD on, nothing to do with DON, V diode on. Okay. What do you think is the resistance of the diode in this particular region? So the way to look at it is, if there is any change in voltage, okay, how much is the change in current? So the change in current is extremely high, okay, because it's almost going towards infinity. So delta V divided by delta I, and you can immediately see the resistance of the diode here is going to be equal to 0. Similarly, you can analyze what is the resistance of the diode in this region when VD is less than VD on. In this case, what we are saying is the ID is equal to 0 no matter what delta VD is below VD on value. So in this case, our resistance of the diode is going to be infinite. Okay. So the model looks like this. For reverse bias, it looks like a switch with VD on plus minus. Okay. And for forward bias, it looks like the switch is closed, plus minus VD on. The on voltage of the diode, or VD on, that depends on the type of diode, what material is used to make this diode. And for silicon PN junction diode, this value is somewhere between 700 to 800 millivolts. I'm going to give you a whole bunch of numerical things, and I would like you to also write down, solve the equations, or do the calculations. What I will do at certain points, since this is not a live video, I will pause at certain point. And at that point, I expect you to do the calculations yourself using your calculator, so that you're, you will be part of the process. All right. So let's take a simple example. What I have is the following. Circuit looks like this. This is V input. I'm applying, and I have a resistor here, and here is our diode. Okay. And this is grounded. The value of the resistance is equal to 10k ohms. And your job is to figure out what is ID and what is VD across the diode. You're given that the saturation current of the diode is given by Is 10 to the power minus 16 amps. Okay. I'm underlying amps because in my experience, when I see students working in the lab, in their lab reports, I have seen many times they forget to write units. Now, units are, I just cannot emphasize enough how important the units are. If you do a mistake in your units, then that answer is completely invalid. I even remember seeing somebody saying micrometers instead of microamps, and they were expecting me to give them the full points for their answer, and this is just a mistake. But in my opinion, it's a big mistake. Okay, so I would like you to pay special attention to units in this course and any other course. In my opinion, if the units are incorrect, then the answer is incorrect. It doesn't matter if your numerical values are correct. Okay. The key point I'm trying to make here is if you make a mistake in units before you graduate from IIT, it will be just that you lose some points here and there, and you will receive less marks. However, if you make mistakes in your units after you graduate from IIT while you're working somewhere else, then it could be quite a disaster. So, I mean, you might be working on designing a circuit for satellite platform or working for ISRO, sending something to Mars, and you make a mistake in units, and you know what to expect. Your answers will be totally wrong. Your equations will be totally wrong. It would be a disastrous consequence. I'm again belaboring this point that units are critical. It doesn't matter which field you work in. It could be in financial domain. It could be mechanical, electrical. Units, you better pay attention. Okay. So in this course, if I see you make mistake in units, then you will definitely not get the credit. The input voltage is given is 2.75 volts. Since diode circuit is a nonlinear circuit, we start with an assumption. So the rule is you start with an assumption, you assume that the diode is on, and then you go back and you verify your assumption if it's working. Diode is on and VD is equal to, we can pick 750 millivolts as a number. Now, as soon as you assume VD is 750 millivolts, then what is the voltage drop across the resistor R is going to be, that will give us ID, which will be equal to V in minus VD divided by R, which will be 2.75 minus 0.75 divided by 10K, which will be equal to 0.2 milliamps. Units important. Okay. The K becomes milli when it comes up. Now we know our accurate equation of the diode. What is the accurate equation of the diode? We know that ID is equal to Is exponential VD divided by VT minus 1. We are assuming, we are saying that the VD is much greater than VT. VT is 26 millivolts for room temperature. Okay. So we can ignore this minus 1 part, because this VD divided by VT will be fairly large number, exponential of that. Okay. So we can say that ID is equal to Is exponential VD divided by VT. We will get VD is equal to VT ln of ID divided by IS. Our initial calculation suggested 0.2 milliamps. So we are going to substitute and figure out, hey, what's my VD value here? So VD value will be equal to 26 millivolts times ln of 0.2 10 to the power minus 3 divided by 10 to the power minus 16, which is the IS. Now I'm going to pause here for you to do the calculation yourself. So I hope you got the answer right, which is 0.736 volts. That's our VD. So it's close to original assumption, which is 750 millivolts. That's what we started off with. Now using this value of the VD, we can once again figure out what my ID is and confirm that everything lines up. Okay. So ID is going to be equal to 2.75 minus 0.736 divided by 10K, and we should get that value to be 0.201 milliamps. So very close to the original approximation. And the reason we get a very close answer is because of this ln of a ratio. Okay. If you see here, that ln gives you this advantage, ln effect. Okay. So this is what our final answer will be. So we will have VD equal to 0.736 volts and ID will be 0.201 milliamps. So as a homework problem, what I have told you is I would like you to do the exact same analysis for V in is equal to 1 volt and then figure out how much current is flowing. You can figure out what ID equal to and what is your VD equal to if V in is equal to 1 volt, and that will be an interesting exercise for you, but you should do it on your own. Now I'm going to go through one of the very important points I want to make in this course, which I have already made it once, but I'm kind of driving it into you. Okay, is the point of small signal analysis and DC operating point. So in this particular case, we are going to talk about DC operating point and a small signal analysis or a small signal model of the diode. Okay, take this previous example again. And so if I apply a V in voltage, okay, I'm going to get certain current ID flowing through the resistor, okay, and I'm going to get a VD voltage across the diode, and V in being the DC voltage. So we can say that, hey, V in, then ID and VD are my DC quantities. And those we can figure out based on the previous analysis that we just did, and then we can get something. These are also called circuit operating point. Now we are going to add a small voltage along with this input voltage V in. I'm going to add this wiggly thing here, and I'm going to call this delta V in. V in is your DC quantity, and delta V in is a small incremental or small signal quantity that I'm introducing. As soon as you introduce this delta V in, what we are going to see is this ID will change and you will get delta ID. Similarly, this VD will change and we will get plus delta VD. Okay, so delta V in, delta ID and delta VD. These are your small signal or incremental. All right. So how do we figure these quantities out? And this is the most important point I'm going to make in this lecture. And if you get this, then rest of the course things will fall into place very well for you. Okay. Let's draw the IV characteristics of the diode. And since the diode is forward biased, we're going to call it ID and VD. And it looks something like this. Something like this, for that matter. Okay. And the point at which we are operating right now is this one. VD DC operating point, and this is our ID DC operating point. And as I said earlier, I'm going to apply the green quantities, which are small signal or incremental quantity, which is delta VD, and we are going to figure out what is going to happen. I'm going to apply something like this. This would be our delta VD. Okay. Since we are applying a small signal over here, I have kind of exaggerated the amplitude just so that it's visible, but it's actually a very small signal compared to the voltage VD. Now, what we are saying to do the analysis is we are saying that in this particular region, okay, I'm just going to draw a tangent touching that characteristics. I'm going to say that the circuit is linear, okay, at around that point. And then assuming that the circuit is linear around that point, I'm going to figure out what is my output. Okay, so the output will be, if you look at this, something like this, then you should see the current will change pretty much something like this. Okay, and so this would be our again incremental output current quantity ID. Okay, so let me repeat this again. We are applying a small signal delta VD riding on top of the DC value VD. Then what we see is we linearize the diode characteristics, which is I'm going to go through that one more time, with a straight line with certain slope, which is tangential, touching at the intersection of VD and ID on the curve. And then we use that slope to figure out what my delta ID is. Okay, so this is all in a graphical format that I'm showing you the small signal analysis, but let's do the actual equation and it will be clear to you. VD is equal to VD, which is the DC part, plus delta VD, and then your ID is equal to capital ID plus delta ID. So these are our DC quantities and these are our AC quantities or small signal. So AC, small signal, incremental, they all denote the same phenomenon we are talking about. Okay, AC is the analysis that you do when you use SPICE also. Now we can write the accurate expression that we know of the diode. In this case, we know that ID is equal to IS exponential VD divided by VT. I'm ignoring the -1 because we already know the diode is conducting and the voltage VD is much greater than VT. The ratio of VD divided by VT is much greater than 1. What we will do is we will substitute for all these values and see what happens. So we have ID is equal to IS exponential VD plus delta VD divided by VT. Okay, and this we can say it's IS exponential VD divided by VT multiplied by exponential delta VD divided by VT. And we also know ID is equal to ID plus delta ID. This being the DC term and this being the AC term. Alright. Now we already know what this parameter is. This is equal to our DC ID. So we can see this term IS exponential VD divided by VT, that is corresponding to the DC ID. Rewrite the expression. I'll rewrite it one more time. ID plus delta ID is equal to ID exponential delta Vd divided by Vt. Okay. The ID being DC term and delta ID being the AC term or a small signal quantity. We will assume that delta Vd is a small signal parameter, so it's much less than delta Vd divided by Vt is much less than 1. Okay. Under that assumption, we can simplify this exponential as ID and 1 plus delta Vd divided by Vt. So it's an approximation. Okay, and here we have ID plus delta ID. So now I can, you can see that the expression even simplifies further. Delta ID is equal to ID divided by Vt times delta Vd. So I can rewrite this again saying delta Vd divided by delta ID is equal to Vt divided by ID. So this parameter is called as incremental resistance of the diode. Now we will put everything together. So pay close attention. So originally we started off with a DC operating point that looked like this. So this is plus minus V in, this is your R, and this is plus minus Vd. And then we figured out what the ID was, or we also call it biasing. So this is the example that we just did, the numerical example that we did. Okay, using that we can do DC operating point. And then once the DC operating point is done, we know that the diode is carrying certain amount of current. Okay, DC current ID. And then we create something called small signal analysis model. Okay, so in this case we would replace our DC voltage source with an AC Vin. Okay, delta Vn. The resistor stays the same. Resistor doesn't change if you do AC analysis or DC analysis. Now the diode part, the diode is now represented, since it's turned on, it's represented with a resistor, and that resistor is Rd. And what is the value of that resistor given by? Is equal to Vt divided by Id. So this is everything putting together, and the value of the voltage across the diode is going to be plus minus its delta Vd, and the current flowing is going to be delta Id. Okay, so let's recap again. When you're given a circuit, any circuit, the first thing is you figure out just by looking at the circuit, is the diode going to turn on? You make an assumption and you say that, okay, the diode is turned on. In our case, it was very easy. Earlier case, it was 2.5 volts. So we would say that the diode should be on. And you know, you started off with a number of 750 millivolts, and then we did a whole bunch of analysis, and we came back with a one level of iteration. What is the value of ID, the DC current, and what is the value of Vd, the DC voltage across the diode? That satisfied our original equation for the diode. Okay, that just gave us an operating point or the biasing for that diode. After that, we are trying to analyze what happens if the Vin changes a little bit, or if there is a small perturbation riding on top of Vn, and we call that delta Vn, which is like an AC voltage applied. Since we have already figured out the DC quantities, we can replace the diode with its small signal model, and in this particular case the small signal model happens to be Rd, which is Vt divided by Id. Remember, this particular Id is coming, it's a DC quantity which we use to calculate this resistance of the diode. We only, in this particular circuit which is on the right side on your screen, there we have only incremental quantities, if you remember. Okay, so delta V in, then delta ID and delta VD. And the value of the resistance is calculated using the DC quantity. Okay, this is because we are linearizing around that operating point. Alright, so this is the way we do small signal analysis starting from a DC operating point. Now, why do we do that? Okay, I mean, if you push this into a simulator, it will give you immediately, you can run so many DC operating points, right? We like to do hand calculations because every time we cannot run to a computer. We can quickly do a hand calculation on a paper napkin and come up with understanding of the circuit, how it works. So to do that, we make these assumptions, and we have to verify the assumptions, but you make the assumptions, you verify the assumption, and then you come up with a very quick and simple answer. When you're doing simulations, the same thing holds true. You will do a DC operating point and you will do AC analysis. The AC analysis part is extremely fast. Okay, for the simulator to do, because it's a linearized circuit. The complete nonlinear analysis of the circuit is going to be something like a transient analysis, where we are calculating, we are doing KCL, KVL and charge conservation, all those equations at each time point, and that can take a long time. May not take a long time for a small circuit, but if you're trying to simulate the whole chip or a really large circuit, then it will take a long time. So that's the reason we like to do AC analysis or small signal analysis even in the simulations, so that we get a quick answer. And it gives you a quick insight about what the circuit is going to behave like. Let me go through one numerical example even for this case so that the point will be clear. Okay, let's start from the previous example. This is a circuit. Please draw the circuits in your book. You must keep a book for this class where you take your own notes, because once you write them, things will be, make sense to you. This is 2.75 volts and I'm applying 10k ohm. Here is a resistor and here is our diode. And we said that the value of the current is ID is equal to 0.2 milliamps, close enough, and voltage VD we said is equal to 0.736 volts. Okay. So these are all DC quantities that we calculated. Let's say that V in has is equal to 2.75 volts plus 100 millivolts peak. Okay, and this is like a ripple or AC quantity. Now our job is to calculate how much of that ripple, this would be your delta V in, will show up across the diode. We know that the diode is turned on, all that analysis we have done. So diode is on and ID is equal to 0.2 milliamp. So this gives us straight away the resistance of the diode, that is equal to VT divided by ID, and that gives you 26 millivolts divided by 0.2 milliamp, and that will be equal to 130 ohms. Now we can draw a small signal equivalent circuit. We will show only the incremental quantities now. This is the thing that you have to remember. This is your 10k resistor representing the diode, which is RD is equal to 130 ohms. Now suddenly the circuit looks very simple. For small signal analysis, I'll pause here and let you calculate what should be the voltage across the diode. Calculate delta VD based on this circuit. It looks like a resistive divider, so it will be RD divided by R plus RD times delta Vn. So this would look like 130 divided by 10k plus 130, and that would, and multiply that by 0.1 volts peak. You can do the calculation. It would be approximately 1.28 millivolts peak. So you can also see that this value is much smaller than VT value. So our small signal analysis, whatever we are doing, should hold fairly well. Even though this on the left side, the delta V in seems like a large value, 100 millivolts peak, but the delta VD across the diode is fairly small, 1.28 millivolts peak. Okay, thank you.